Welcome back to this series of demonstrations on programming STM32 series of microcontrollers. In our previous videos and demonstrations, we have set up a basic board of Proteus simulation that we can use to test the programs written for STM32 series of microcontrollers. However, the same programs can also be run on the physical hardware, and that is actually more desirable that you actually run the programs on physical hardware. However, it is more convenient just for demonstration purposes and just for teaching that we use this simulation software as well. So in the last video, we were talking about the basic setup of the GPIO pins. So before embarking on the series of various uh, techniques to use these GPIO pins, I think it is more um, fruitful to have a little bit of in-depth discussion on what the GPIO pins are and what they can do, etc., etc. So that whenever we talk about something, you should not be surprised that this is something new for you. Um, Although we will be using the some libraries and easy to use components already developed by STM Microelectronics and other resources. However, in order to be more productive and more in control, it is better to have some understanding of what you are working on. So let's see. I have made a little presentation on this. So we will be talking about this presentation. So your microcontroller, when we are talking about STM32, as you know, it is a huge family of microcontrollers, and there are a number of families in it. So we are talking about the simplest one, which is easily available, not very expensive, and it is you can buy a board which has this microcontroller on it, which is called Blue Pill. I will show you the picture of Blue Pill later on in this presentation. This is the microcontroller, actual microcontroller. This is an integrated circuit um, which has 48 pins. So the number is STM32F103C8. So as you can see, the various pins are, some pins are for power supply, like this VSS and VDD are power supply pins. And then this is the pin uh, for the external battery to power the real-time clock, which is built inside this microcontroller. And then these are the pins PC14, PC15, PD0, PD1, and PD0, PA0, PA1, PA2, PA3. These are the GPIO pins. GPIO pin stands for General Purpose Input and Output Digital Pins. We will talk about these pins later on. And actually, these pins actually have multiple functions as well. Not only that these are for general purpose digital input and output. Some pins have a serial communication with them. Some pins have I2C communication. Some pins are for analog to digital conversion. So these pins they tend to have multiple functions, and you can select one of the functions at a time, and that is all configurable within the microcontroller. So the same picture, a little bit more clear, I hope you can see. So this is the picture of STM32F103C8 microcontroller. And you can see the power supply pins VSS and VDD. This is also VSS-A and VDD-A. Both these are also power supply pins, but these are actually for analog circuitry. They have been kept separate from these pins because the digital circuitry tends to have a noise when it switches on and off. And analog systems, they usually require a very clean power supply, which is free of this noise. So most of the times when you make your own circuits, which are more sensitive sort of circuits, and they need a clean power supply to the analog circuitry, you provide a specially filtered power supply to these things. But in most of the cases, you can just tie these together. This VDDA and VDD can be tied together. This VSSA and VSS can be tied together, and you can give the same power supply. Again, here is also the VSS and VDD power supply, VSS and VDD power supply. So there are multiple pins for the power supply. Um, Then there are certain pins like this RCC oscillator in and RCC oscillator out. Here is the you can apply your external crystal oscillator to give the oscillator signals to this microcontroller, and then we will see later in a later presentation how to configure the oscillators in this or clocks in this microcontroller. This just to be brief, this microcontroller has a built-in 8 megahertz oscillator, so you can just get away with these things. Just you don't need this oscillator, external oscillator, and you can use the internal oscillator. However, if you want more precise clock signals and you want to leverage the microcontroller up to the normal of the maximum 72 megahertz speed, I'm sorry, you have to put in an external oscillator here. Anyway, because this discussion is not mainly about the hardware setup, this is basically about the software setup. So GPIO stands for General Purpose Digital Pins. So these pins, all which are grayed in here, these are the general purpose input output pins, and both all these pins, they can be configured either to accept an internal external signal or to give out a signal from microcontroller to the external circuitry. So when the signal arises from the microcontroller and appears on this pin, this is called output. And when the signal is coming from outside and microcontroller reads whether the digital pin is receiving a logic 0 or logic 1 signal, then it is called input. So although these pins, they can also assume the analog circuitry, analog functionality, but when we talk about GPIO, that actually means a digital setup that each pin can be set to either logic high or logic low. Logic high is 3.3 volts, as its power supply is 3.3 volt power supply. So logic high will be 3.3 volts and logic 0 will be the 0 volts or ground. So each pin can also have alternate functions that we will see later. And all these pins, they are not 5 volt tolerant. Almost we should assume, because this is a 3.3 volt microcontroller. So the maximum input voltage coming as a signal to these pins should not be 5 volts. It should be 3.3 volts. So if you are giving it a signal from another microcontroller like Arduino or something else which has an output of 5 volts, so make sure that which pin you are connecting to, can that pin be tolerating this 5 volt signal or not. And in any case, more than 5 volt is not tolerated at any levels. The maximum current that a pin can deliver is 25 milliamperes. So 25 milliamperes current it can be drawn from each pin maximum, and from the all of the pins combined together at any given time, you cannot take about more than 200 milliamperes from this microcontroller itself. So it is basically not meant for powering the things, it is meant for giving out signals. And when your device like LEDs or motors etc., they need more power, you use external transistors to boost the power. The pins are grouped into ports, and the ports are like GPIO-A, GPIO-B, GPIO-C, GPIO-D, and so on, depending upon how many ports a particular microcontroller has. So ports are grouped as GPIOs. So like this PA0, PA1, all these pins, they will be grouped into GPIO A port. And these ones which are numbered as PB2, PB10, PB11, these will be grouped into GPIO B port. So each port has a number of registers to control the functionality of the pins. So these pins have multiple functions and multiple configurations. So these configurations are set by a number of registers, which are memory locations associated with each GPIO port. So you have to configure various bits in various registers to get a particular functionality. So, although that is a desirable feature and desirable way of programming, but that makes the programming of these microcontrollers a little more technical and a little more demanding. So, in order to make it easy, the STM Microelectronics have produced a set of libraries which are called HAL libraries, HAL, Hardware Abstraction Layer. So these libraries, they accept commands in simple parameters, and they actually translate to those various registers at the lower level, which is abstracted from us and makes the programming easier and more fun. But nevertheless, you can always dive deeper into the registers and access them directly. So each GPIO pin can be configured as an output pin, either as an input pin or as an alternate function pin. Alternate functions are like they can be digital functions, but they are special functions like serial communication, like um uh, CAN bus communication, I2C communication, SPI communication, etc., etc. So each output can be configured as push-pull, open collector, and its initial state. So push-pull is this is the output control system, and there are two transistors attached inside the microcontroller, each pin with each pin. If we are talking about one pin here. So if this configuration is attached as both a P channel and N channel MOSFETs are attached, then this is called push pull. So this pin can assume both 0 and 1 states. So either you can switch it to 0 volt or 3.3 volts. This is the push pull configuration. Or we can connect it only as an open drain. In open drain, this transistor will not be functional, only this transistor will be functional. So the pin can either be only 0 or in an open state when we set it to high logic or 1. Similarly, when you are talking about the input stage, each pin can have a pull up resistor or a pull down resistor. That is usually we use external pull up or pull down resistors, but these have both resistors inside it. So we can use either a pull up or pull down resistors inside the microcontroller. Uh, we'll talk about the speed later on, and we have talked about the alternate functions. So this is the pictorial representation of a microcontroller, that this is the output register of a port. Like we will talk about the output register in our STM32. So that register is actually a memory location. So whenever you set a 1 in a bit, the corresponding pin sets to high, and whenever you set 0 to a bit, the corresponding pin turns to low or 0 volts. So inside the microcontroller, you actually set high and low in these register bits, and the corresponding pins, they get logic high or logic low, or 3.3 volt or 0 volt output. So just to give you an idea that each port, like GPIO-A, has a number of registers. Two of those registers are output data register ODR and input data register IDR. So whenever you set a particular pin like ODR 0 as high, the corresponding pin will turn high. And when the data arrives at that pin, you read the IDR 0 pin, and in this IDR register to get if the pin is high or low from an external signal. So all this complexity of these pins will be hidden to us by the presence of or by the use of these Hall libraries. But nevertheless, it is important to know if these registers are present, and we can also sometimes use these registers directly to access the microcontroller pins. So this is the actual IC STM32F103C8, and this is the commonly available board which has all the basic circuitry already attached, and all the IO lines, they are given as header from here where you can attach your circuits or your other devices. So here is the microcontroller, and here is the 8 megahertz external crystal as well. These are the pins used to attach the programmer to program it, and these are the two jumpers which are used to use the bootloader. If you don't want to use this programmer, you can use the internal bootloader, and for that you have to set this position of these pins. So this is the USB connector. This microcontroller has built-in USB 2 module, so you can make devices that are actually appear as USB devices to your PC or other things. So these pins like G, these are ground pins. 3.3 is 3.3 volt, and R is the reset pin. And rest of these are, this is PB11, PB10, PB1, PB0. These are the same thin lines as you can see here. These lines, PB10, PB11, and PB0. I don't know where it is. PB0. Here is PB0, PB1, PB2. These are the lines which are appearing here on these pins. So, and this is the 3.3 volt ground, 5 volt, and so on. There is also a one LED attached on this board, and which is connected to PC13 pin of the microcontroller, so that you can make a quick program to test this LCD as on or off. And here is the power supply LED. So this is the map of this blue pill board. This is called blue pill. It's just a name, nothing special about it. There are many other boards available in market based upon this microcontroller and other microcontrollers, but this one is very economical and easy to get from your local vendors, even on online stores. So this picture you can download from internet, and there's a number of other people who have developed these pictures. These actually shows the pin numbers, like this is PB12, PB13, PB14, PB15. These are the pins connected, and they like 5 volt ground, 3.3 volt. This is for battery, and etc, etc. Another thing important to know is that certain pins which have this solid dash shown here, these pins are 5 volt tolerant. So you can give a 5 volt signal easily to these pins. But these pins which have a hollow dot on this side, these are not 5 volt tolerant, and you can give only up to 3.3 volt signal on these lines. So beware when you are connecting your board or physical hardware to some other microcontroller or some other sensor or something like that. So you should know that the signal coming should be 5 volts or 3.3 volts. These are the various other tasks or other functions that are associated with these pins. Like this PB13 pin is also act as serial clock 2 pins, and it can also act as T1, C1, N, and CTS3. These are various functions which are written in the data sheet, and we will come across those later on. Here is the programming header, which is actually PA13 and PA14 pins, but you can attach the external programmer to this header to program it. We'll show you later. So this is the external programmer which is available very easily. This is Chinese made programmer which is called ST-Link. So you get this ST-Link programmer which gets connected to on this side to the USB port of your PC, and from this side using these jumpers to these jump headers on this side, and then you can write your program in Cube IDE, and that program will be transferred directly to it and execute. Also, you might need this FTDI 232 USB to serial adapter. This is also useful not only for getting the serial data from your microcontroller, but also sometimes to program it over the serial port without using that FTDI, that ST-Link programmer. So this is also a useful thing. You should get it. So this can be the useful settings in which the ST-Link is attached to this header, and this USB to serial converter is attached to this serial and transport communication. So this completes the setup in most of the cases. It is also advisable or useful that you can have these small breakout boards, homemade breakout boards of these, like these are 8 LEDs connected through current limiting resistors and as a header, so that you can attach your microcontroller pins using jumpers and see how the LEDs and GPIO pins as output signals you can see them. We will be using another technique which is called the simulation. We will be using the Proteus software to simulate it. So here we have this microcontroller board, a microcontroller component, a reset circuit, and we have this 10 LEDs connected through current limiting resistors to these microcontroller pins as we have shown you in the previous video. So that's all. Thank you very much. I hope this basic presentation or basic discussion will go a long way with us, and when we will be starting the actual programming or uh, actual coding, so that the things become easier for you and for me as well, because whenever I talk about something new, I feel it's something strange that I have not told you people about this thing before. So we have discussed sufficiently the basic things, and whenever we will come across some new features or new things, we will discuss those right there. So I think we should stop here, and next video, inshallah, we will be talking about the STM32 IDE and writing some applications for these LEDs as GPIO pins. And there we will see how to set the various features of these GPIO pins. Thank you very much. May Allah bless you all. Allah Hafiz.